My name is Charleste King, and today we're going to be talking about MySQL architecture options and which architecture is right for you. Um, Let me tell you about myself a little bit. The lead DBA for MySQL at Dataville. I have over 15 years experience and about 20 some odd years in IT in general. Dataville Corporation that I work for is a company that provides onshore offshore database services in a myriad of RDMSs. So what is a database? A database is a collection of information that is organized in such a way that it can be easily accessed, managed, and updated. So original databases probably originated around the time when we used cuneiform and the library at Alexandria with scrolls and papyruses. File cabinets are databases, and that is in the basic sense. So what are the goals of a database? When we have a database, what we want is we want data to be safely stored, and we want it to be something that we can retrieve our data when we want to and in the manner that we want to. And we can have systematic and repeatable functionality for that database and on our data. And we want it to be as fast as possible. So when we talk about data being safely stored, we want to make sure that it's protected, it does not become corrupt, and it is not changed without our instructions. So being protected can mean any way, where from making sure that the prying eyes can't see it, to make sure that it is secure and it is not changeable without what we tell it to do. We don't want it to become corrupted just by sitting on disk and having system issues happening to it. We want it to remain intact. We also want to retrieve our data. We want to be able to find it, and we need to be able to cross-reference our data, and we want it to retain its integrity. The biggest problem people have nowadays with our databases is finding their data and cross-referencing in a speedy manner so that we can obtain our data in a usable fashion, and that is what our goal is. The systematic and repeated functionality that we want, we have a way to systematically store and find our data. We want to be able to send some instructions to alter our data, but we want it to be done in a structured and repeatable way. We don't want randomized things to happen to it. We want it to be predictable. We want to know what is happening to it. Of course, there are caveats when we're talking about random things, but those are a specific thing. We expect randomness to happen when we use a random call. Now, we want it to be as fast as possible. And there's different methodologies for storage that have pros and cons. So we have long-term storage, which is safe and archival, but it's typically slower to obtain our data. We also can have short-term storage, which has the pro of being really fast to retrieve, but is less safe. It is not static. It is not stored in any way that is good for long-term archival methods. And then we have standard term storage. So basically for these three things, what you could think of them are as long-term storage is like tape or printout even. Short-term storage would be in memory, very fast, but if the system restarts, then that's lost if there's no more power to the memory. And standard term storage would be a hard disk of some way, shape, or form, including SSD and regular disk. So where is the data kept? There's different places that we can keep the data, and we talked about the different kinds of storage already. And then there's methods of storage, and then there's formats of storage. Methods can be how it's written, it can be the format it's written, it can be anything that's a way to differentiate our data from the background. Formats can be, are we storing it in a particular storage engine? Are we storing it, excuse me, so that we have different data types in different formats? So all of these things are items we need to keep in mind. Now, regarding storage engines, in MySQL, we use the terminology storage engines. These are the different types of storage that we can use. they're the different methods and formats of storage for MySQL. So we have transactional and non-transactional. Those can also be called atomic. Um, so transactional is basically you can have a block statement and you can have a begin transaction and end transaction around it as a wrapper. And if something fails in there, everything gets rolled back for the whole larger group. And in a non-transactional or atomic storage, the data is altered as it goes through the statements. So if you send a statement, it's committed. Now, how data has been stored in the past, we've had lists and linked lists. The linked list can be considered one of the mother of all models. It is where you basically have some kind of index or key, and then you have your data point, and then you have a reference to another row in that table, some other key, and then you can recursively keep finding your data that's related to one another. You can also have flat files, which is very common when you're doing database type of work in programs. Um, if anybody has done any kind of programming, there's a lot of times when you're going to write to a flat file. I just want to go back to the linked list. If you've ever written programs in Perl or Java and you have a list, or any other kind of programming language, and there's a list that you're storing data in, that is also a linked list. And the flat file would be the file that you write things to, and then you're going to scan and look for your data and retrieve it. So even in MySQL, you consider the most simple flat file storage is our configuration file, where we have a parameter name and then a value. And then the configuration file that gets read one time when the system loads, and there is a flat file data set for you. Traditionally, we also use spreadsheets, and these spreadsheets can be used to contain data. They have rows and columns. You can infer relationships, and in modern spreadsheet programs, you can reference even between cells and do links that way. Hierarchical databases, those are the old school kind where there's a start and a finish. If you ever look at relational databases, data model compared to a hierarchical database model, you'll see that that there are relationships in a relational database, and there is no beginning and end. Whereas in a hierarchical database, there's more of a beginning and an end. Our modern data storage concerns are typically storage size, memory, indexes, and redundancy. So we want to talk about how big can we get our data to be, how small is our data going to be, how much memory we're going to be using, how much memory are we supposed to be using, indexes, we don't want to have so many that it's not useful or it slows the system down. We want to have enough so that we can find our data, and redundancy in the sense that we want to be able to make sure our data is going to be there if there's some kind of failure. There's a number of different storage types in MySQL specifically. We have MYISAM, INNODB, memory, NDB, CSV, and ExtraDB are the most common. There's a few others that I'm not going to talk about today, including things like black hole, which are really handy to use during certain types of usages that you might have. For example, a black hole engine is useful, like if you're going to say upgrade for an old MySQL 5.0 instance to 5.6, and you want to use replication because you want to have minimal downtime, then you can use black hole engine just to be able to write the binary logs and do your daisy chain replication, so that you're not having to pay for all that storage for the 5.1 and the 5.5 instances, and then you can have your replication and be able to use it without too much cost. But we're not going to discuss that today because these are the most common. ExtraDB is actually used with Percona and is with GALERA cluster specifically, but the others, MyISAM, INNODB, memory, NDB, and CSV, come from the MySQL, which is now owned by Oracle, from that camp. MyISAM was the default storage engine from when I first started using MySQL around 3 up until very recently. It is a non-transactional or atomic storage engine. So that means that, again, when you submit a statement, it gets processed right then and there. It is very fast for retrieval. The caveats for this are that when you specifically you have problems of when you have row locking versus table locking. So the entire table locking for is done for MYISAM. So that happens when you're doing backups, when you're inserting, updating, and deleting. So if somebody else is going to want to do something to that table, it has to wait its turn. So when you have a very high transaction environment, MYISAM becomes a bottleneck. Also, when you're doing backups, then MyISAM becomes a bottleneck because you can't do a hot backup off of MyISAM and maintain your state of your backup if you want to be doing this properly. And then the only reason right now to use MyISAM, now that we have 5.6, is if you're going to be doing delayed inserts. That is something that MyISAM is the only thing that can do at this point. And other than that, I would recommend you use other storage engines. The one that we normally recommend to use is INNODB. This is the now default storage engine for MySQL. It is transactional and ACID compliant. It uses row level locking, and before 5.7 it uses gap locking, so that it just locks the row that it's on, and then it will lock the next row or so that it will have places for concurrent data or consecutive data, excuse me. And then so you can take a hot backup of it because you're not going to be losing state. It has multi-version concurrency control, which means that when I'm modifying a row and another function is coming into, a statement is coming in that wants to access that row, what it's doing is that it's marking the old row as basically old and archived, and while it's doing the functionality elsewhere where it writes it, and then it will go back and remove that so that we won't get those dirty reads if we don't want them. So the biggest caveat for INNODB is compression. It doesn't work well for fast access. Another thing to think about for INNODB is if you're going to be using something like GALERA cluster, you can use INNODB for that as well. CSV. This is a handy storage engine to use. It is basically a text file, comma separated values. These are the classic. You can open them up in Excel. You can open them up in your text editors, and it's the same thing. Something that you could have worked with in the 90s, you can read it now. It's always been available. It's easily used by software. You can write a little script that will be easily able to access it using no additional libraries. It just opens a file and you can read it and you can scan it. These can be a very handy way to allow programs to be able to access your data if you don't want to use a specific RDMS or something on the application, the software, then you can connect to CSV. Memory. The memory storage engine is very, very fast. What happens is that all of the data in the indexes is stored in memory. The problem with it, the caveat, is obviously that it is not stored anywhere physical. So if the memory loses power, whether it's from a restart or catastrophic failure, the data is not retained. So that data is normally something that you just want to keep in memory. That's not going to be something you're going to want to have later. It could be handy for holding session data, make it much more fast. And it's also very quick to query. INNODB is the storage engine used with MySQL cluster exclusively. It's used to store the data in data nodes, and the data nodes are managed by the administrative node. In addition to this, ExtraDB, that was written by Percona, and that is the storage engine that's used for. When we look at our different kinds of storage engines and compare them, we're going to be looking at the maximum storage limit, transaction types, foreign keys, multi-version concurrency control, data compression, scalability, ACID compliance, and parallel writes. So when you look at INNODB, it can have a limit of storage of 48 terabytes. INNODB has 3 terabytes, and MyISAM is limited by disk and file size. Transaction types for INNODB, You can have all kinds. INNODB has to be read committed, and MYISAM is atomic. As we talked about before, that means that there's no transactions. It's just a statement is run as it's written and it's sent. Foreign keys INNODB has. INNODB only has after 7.3 or later, and they are ignored by MYISAM. You can keep your foreign key statements in there. It will remember them, but it doesn't do anything with them. So it will still be up to you in your code to enforce foreign key constraints if you're using MYISAM. For data compression, you can do it inside of INNODB. It's not very quick, but you can do it. And INNODB does not have it, nor does MYISAM. For scalability, you have to use application level sharding for both INNODB and MYISAM. Scalability for INNODB is because you can distribute amongst nodes, and there you have it for scalability. Of course, you can also use application level sharding for INNODB as well. Acid compliance, yes for INNODB and INNODB, and no for MYISAM. Largely because it is atomic, MYISAM can't be acid compliant. Parallel writes, you cannot be writing two threads at the same time in INNODB and MYISAM, but you can with INNODB. Did not compare CSV or others with these items because they're largely not used. ExtraDB has its own parameters. They weren't too easy to find the specifics from Percona. So our different cluster solutions are GALERA and MySQL cluster. And we're just going to take a few minutes to discuss them both. They both have features that are very nice, and they both have a few issues. MySQL cluster is synchronous. It's synchronous in its replication in theory, and it is highly scalable, real-time, ACID compliant, transactional database. The claim is 99.999% availability. It's distributed with a multi-master architecture with no single point of failure. It scales horizontally, and it has both SQL and NoSQL interfaces, and it uses the INNODB storage engine. So one of the things that means about the multi-master architecture with no single point of failure, you can set it up that way. You can set it up with like one data node, one management node, and one API node, which is where you run MySQL from the command line and access the data from. Ideally, you would have at least 2 data nodes, if not 3, and you could even have multiple management nodes and as many of the API nodes, the MySQL nodes that you would like. Typically, people will install the data node and have the API node on each of those instances, and typically people only have one management node, but there is your single point of failure. So you would want to have at least 2 excuse me, management nodes if you wanted to have no single point of failure. So, but then now you're talking about right there, if we're going to have 2 data nodes, 2 management nodes, you have 4 servers you need to do this. And then, but typically people prefer to have 3, so there's that multiple redundancy. So you have at least 5 servers there that you're going to use. And if you want to keep your API nodes separate from your data and your management nodes, then those are additional servers that you need to stand. Another thing to think about with MySQL cluster is latency. Because the way clusters work, if you submit a transaction, it needs confirmation that everybody knows that the transaction is completed before it's called done. So you can get some inherent latency there. While supporting MySQL cluster, there have been a number of times where difficulties have occurred, to put it lightly. For example, we've had clients that just today, I had a client that was having a problem with latency, and they wanted to see where the problem was, where the bottleneck was. So we went and looked in there, and then I noticed that in the error log when I was looking around that there was corruption in one of the data files for a table in their database. So when I looked there, I decided, okay, I'll go look at the other node, and yes, that had propagated. And the problem was because it had run out of disk space on node A, and that corruption, that problem that occurred, synced with node B. So now there was corruption in both nodes. So even when they increased disk space on node A, you still had that corruption, and the repair was unsuccessful. So we had to restore from backups. And this was an emergency call that we had to deal with. Another time with another client, with the version of cluster that they were using, anytime you try to do an online add to a node to the cluster, it would cascade in data failure. So some of those things that are supposed to be the important things with cluster that, for example, you should be able to do this hot add and drop nodes so you can do maintenance on each node. That's problematic at times. And you can get some things propagating that you don't want to have propagated. When it's working, it works beautifully and it's fabulous, but it requires a balancing act to get it set up, and you have to make sure that it's solid, and you have to be ready to manage it consistently. For Galera cluster, it has synchronous replication, active multi-master topology. It reads and writes to any cluster node. Automatic membership control, failed nodes drop from the cluster. Automatic node joining, true parallel replication on row level, and direct client connections, native MySQL look and feel, and you can use the INNODB or ExtraDB storage engines. So how this differs from MySQL cluster, Galera cluster uses no management node. In your cluster, you have each of the different nodes communicating to one another. The problem there becomes latency, because if you have many nodes, then you're sending a large transaction. That entire transaction has to complete on every single node, and they all have to report back to each other that it has been completed before the data is considered committed. It makes it very, transactional and ACID compliant, which is great, but you can have some inherent latencies. You can also use it so you can write to one node and have it propagate and use the others kind of as backups, or you could do all your writes to one node and do all your reads to another node, or however you want to do read-write splits or whatever, whichever way works best for you. Another solution is replication, and that's using the standard MySQL. You could be using Percona, MariaDB, MySQL, Oracle MySQL. The standard architectures are master-slave, master-master, master-multi-slave, and ring replication. Because I abhor ring replication so much, we're not going to really discuss it today. Let's just overview ring replication. That's when you have master slaves, because you can only have one master for a server. You can have many slaves, but one master. So server A is a master to server B, B is a server master to server C, and C is a master to server D, D is the master to server A. So whenever you want to pull somebody out of that ring and to maintenance or upgrades, then you can see that the problems, you have to stop replication, and then you have to bring that other one in and basically have a very long slave chain before you get them all synced up, and then you have to turn on replication again back to the master. So it's pretty complicated. So we're not going to go into deep detail on that, but it does exist out there. Master slave is one of the most common ways of standing up redundancy. Master slave is where the readability of the slave is without impacting the master. The backups can be taken without impacting the master. Downtime can be averted when the slave is taken offline for maintenance and easily resynced. It's asynchronous replication, which is a sticking point for some people, why they want to go with cluster. People want that synchronous replication, but again, remember that goes with those transactions. There's no automatic failover in a master slave or any replication, really truly. There's some downtime and possible data loss if the master fails. How replication works is when the master, as transactions happen to it, don't care about the selects, we talk about the reads, writes, updates, deletes. There's a binary log enabled on the master. That information is written to the master. You can have row level replication, which it will write the rows, and you can have statement where it will write the statements. Typically, people prefer to use mixed, because then when there's something that's unsafe for replication, where, say, for example, somebody sends a statement, update my table, set date equal now. Now the function INNODB with parentheses would then write the date right now when you ran that. But on the slave, if it read that now, it's going to be a different time and you have data divergence. So if you set it to mixed or to row based, what it will do, it will write the actual values for those rows, since that was not safe. However, if you wanted to use statement based, sometimes you do. For example, when you're doing large transactions and you don't want to have the slave read everything. So I say update my table, set my flag equals 1, where something, something, something. Now, if I send that, and I say that's going to impact 1,000,000 rows, it's going to be much more efficient if I just log that statement and then the slave reads that statement, runs that statement, than having to read 1,000,000 rows that get changed. So typically you want mixed. The master-slave architecture, this diagram I have over here on the right, it shows a master and 2 slaves, and one of the slaves has that text is supposed to show you backups. So you would typically, you can have a single slave or you can have 2 slaves basic, and so that way you can also use this for read-write splits. There is obviously a possibility of there being lag, so your reads could be missing data that's not current. And ideally you want to have your replication so that your slave is not very far behind from the master. Typically the biggest problem with slave lag comes from when you're first standing up a slave, and then you have a large database and you finally took your backup and you load it into your slave. Now it has to read through all those binary logs and say something big happened on there. But some people's architecture are inherent to slave lag, and so you have to determine where a problematic threshold is, because if you have your slave and if you can keep your binary logs, then you actually have all of your data after it was written. So that's still a good reliable way of making sure you have no data loss. Master is a little bit differently. Each master is a master to the other one. So A is a master of B and B is a master of A. You can have slaves off of those, additional slaves off of either one of those. The rights can be distributed. So you can split it however you like. If you put a load balancer in front or use a tool like MMM or some kind of proxy, HA proxy, then you can tell it to split your writes, you can tell it to split your reads, or however you want to do it. If you're using some kind of load balancer in front, it's very efficient for failover if something has to be taken down or something goes down. MySQL is automatic on that side because it's already a master. There's no promotion needed. When a master slave, you have to promote the slave to a master, so you can keep your state up. So when we are also talking about master slave, then we can have multiple slaves, and so we've had enterprise customers with hundreds of servers using master slaves with it in various configurations, and we've also had people just have 2, and either one can work for you for some redundancy. And master just allows you to have that promotion being unneeded. The caveats to master is you have to have a stepped primary key. So when you have that auto increment, so master A, it does its keys as like 1, 3, 5, 7, and master B will have 2, 4, 6, 8. And then if you have more in the multi-master type of realm, if you want to do some kind of ring replication, then you would have to have an offset again. So you might have 1, 4, 8, and then 2, 5, 9, that kind of thing, and then so that you can have more servers in there. It is asynchronous as well. It is more complex than master slave to deploy, and once you've got it going, though, it can be very simple, just like master slave. So that isn't another option for you. For performance enhancements, you can have with these are read-write splits, reporting backup splits, and then you want to look at your IOPS and your memory. So these are different things that you might want to look at in order to improve performance for you. So if you're spending all of your time on your resources on your server reading the data and you're trying to write it at the same time, then you can be using up all of the resources. One of the biggest things that we find causing problems for clients and people calling us saying, oh no, there's a problem here. It's so slow. Why isn't the database responding? One of the first things you might check besides seeing, is it up? Is it running? Is, are there reports being run? Is there a backup going on? They take so much of the system resources and they can lock things up a bit too, especially if you have MYISAM, if you're doing backups. And then when you're doing reporting, that can use a lot of the resources because normally people don't have a very simple report. People typically want to do these complex queries and it's writing temporary tables and whatnot. So this is another reason why we recommend having a slave for reporting and backups. You could use one, so if you have a master slave configuration and that's all you can stand up right now, you have your master for your application for reading and writing, you have your slave, you run your reports and your backups off of the slave, plus you have the redundancy for of the slave that you can promote to master. It's simple, it's effective, and yes, there can be some lag and it's not going to be automated, but you're covering most of your bases there. Another thing to look at is IOPS. Because we have IOPS problems with people going, how much can where's the bottleneck here? And what kind of problems am I having caused by slow IOPS or fast IOPS? And also memory. How much memory do I need? How much am I using? That kind of stuff. So for our read-write splits, as we talked about, even with a cluster, you can stand up a read-only slave to split loads of reads and writes. This is works particularly well with a master-slave or master-master architecture. I really recommend that you stand up at least a slave for your backups and your reports, as I talked about before. It can be useful for rewrite splits. And for reporting backup splits. This way will keep your data free. It won't be locking things, especially if you have MYISAM, and you're not going to be tying up those resources. Now, the kind of disk you're writing to is very important because even in the cloud services, people will think, well, I'm just sharing this giant server with these other people. And, the problem comes with how fast can you seek and write and all of that to the disk. So for example, if we did a test even using RDS, the difference between using provisioned IOPS and using the standard configuration for the same size of instance is very marked. It's, at least a 25% improvement in performance, even for really thrashy things. If the difference between SSD and a disk for a regular server is also marked as well. You'll find though that there are going to be certain data types that it's not going to data sets, excuse me, that are not going to be improved with their performance with it. That's because you may not be doing seek, so that might not be your bottleneck. So that's why you would have to look at the entire environment to see where your bottlenecks are. But typically we'll say the faster you can get, the better it's going to be. And you can eliminate bottlenecks from that. So SSD is the current best technology for speed, and we love our customers that are using SSD. Now for speed, GALERA MySQL cluster and MySQL 5.6 have all been benchmarked, and there are different kinds of benchmarks. So they're kind of talking about apples and oranges. So GALERA has been benchmarked around 80K transactions per second. SQL 5.6 is 250K average for INNODB specifically, and cluster can do 2.5 million queries per second. That's not, those are just straight selects, and 200 million queries per second for NoSQL. And if you're not familiar with NoSQL versus SQL, NoSQL is a different type of structure. So like MongoDB is a NoSQL database engine, and you store things in documents and pages, and your queries are a little bit different. You're not using the select star from Bob. So it's kind of difficult to compare with these different benchmarks. Excuse me. Compared to, it's difficult to compare the different benchmarks that have been provided by various people, but this is the closest thing we can have to actual benchmarks. So you can see what the different kinds of transactions are promised and queries per second, and make the right decision for you. Memory is key, as with any database engine. Having enough RAM is of utmost importance with any database. Storage of keys, index, and even data can greatly improve performance. For example, if you're using INNODB, you throw any available memory after tuning to the buffer pool, and for MYISAM, you make sure the key buffer is sufficient for your indexes and keys. Always ensure you do not vastly over allocate memory to avoid swap. This can be very problematic with hyperthreading as well, so you need to check that hyperthreading. It should work well with the newer versions of CentOS and MySQL, but there were problems before with like CentOS 5 and like 5.155, so keep your eye out for that kind of thing. Another thing to remember is that if your buffer pool is large enough for INNODB, you can stuff all of the data you can in there. If you have, only, a gig of data that you're running in a database, and you have a couple gigs of memory for that buffer pool, it can throw all the data and the indexes in that memory and make it wicked fast. It's still going to be writing to disk because it's in INNODB, so it can be really handy. And then for MyISAM, that key buffer is where it keeps the indexes and whatnot, so that can improve performance there as well, so we'll know where to look and the seek time goes down. For high availability, you need failover ability and you need data redundancy. And the data redundancy keeps you from having data loss. And for failover, you need to be able to have your system up and running as quickly as possible, and hopefully with little to no interruptions. So failover, we're going to talk about standalone instances, master slave, master master, MySQL cluster, and GALERA cluster. So for standalone, a full consistent backup is required. For failover, you need binary logs for point-in-time recovery from your last backup. So even though it's not slaving anywhere, you still want those binary logs so it can record the transactions that have happened. Your restoration is going to take time, especially if you have a large data set. You're going to have hardware available to be able to restore it. So for example, if you have a server and it's a motherboard failure, and if you don't have those binary logs and shadowed and that backup is not fresh, you could potentially have a long downtime while you wait to get that data back. There's a high probability of data loss if no binary log, and there's still a good probability of some data loss even with that, considering what kinds of things could go on, and your downtime for your company could be pretty high. For master slave, you have a hot standby. There is no immediate restore required. There is possible data loss if the slave is not in sync with a master, and you need to have some kind of methodology to promote the slave to a master. You might need an IP change, an application connection change, or a load balancer. So, and then one of the caveats with a master slave is that, remember, if you have to promote the master, and you don't want to have a load balancer that's going to go, oh, the master's up, let's switch it back there, because if you've already promoted the slave, you have to resync that master, because now it's going to have to come in as a slave to be synced before you can promote it back up. So if you have a load balancer that's going to take note that the master is down and switch to the slave, you want to leave it there until you manually move it back, because you know that it's fixed. So if you can use some kind of VIP, floating IPs, whatever, that can make things a lot quicker for your application. But then of course that requires a load balancer on it, or proxy. Master, you also have a hot standby. There's no immediate restore required. There's no promotion needed. Again, you either need some kind of proxy, load balancer, or an IP change, application connection change that you will need to use in order to have that change come into effect. And then, of course, you will obviously, in both of these environments, want to fix the server that's down as quickly as possible so you can keep your redundancy and have all of the tools available to you that you're used to having. So for MySQL cluster, it's an automatic internal failover. Replicants of those are manual failovers. The nature of MySQL cluster means that with the management node, multiple data nodes, and multiple API nodes, there is still a single point of failure with the management node. So there you go. For GALERA cluster, remember there is no management node. It is an automatic internally done failover. Replicants also have a manual failover. If the application is going to a particular IP in lieu of a pool, then a floating IP or a manual failover will be required on your application. And because again, a lot of people just like to point their applications to a single node. And if you're using some kind of load balancer or virtual IP, floating IP, then you can at least move that to a different server so that you can keep that up with little to no problem. For data redundancy for standalone, master slave, master, MySQL cluster, and GALERA cluster is another thing that we need to make sure we have done properly. For standalone, there is no real data redundancy. The dependence is on the backups and binary logs, and there's a high probability of data loss in some kind of failure. And again, you would have to restore the whole system, and hopefully you've got those binary logs shadowed somewhere so that if there's a catastrophic failure, you can at least restore the data to that point in time. The master slave, remember the slave is a hot replica of the master. It's a hot backup. It's on standby. The possibility of data loss still occurs with slave lag. You can get binary log corruption, which can cause data drift or data loss. Then you can't replicate something when it's corrupted. Improper binary logging and the use of triggers can cause data drift. So for example, we were talked about before the binary log safe statements and unsafe statements, those time things like now and whatnot, and triggers, because if you're using row-based binary logging and you use a trigger, that trigger is not going to get triggered on the slave. So you have to send it the statement so that it can execute the statement and execute the trigger on the slave. So there's some caveats there. So if you're really into using triggers, you're going to be using statement mode in your binary logging, and that means that you're going to want to stop using those unsafe replication statements, the nows and the times and all of that kind of stuff, the relative things that are depending on the RDMS to use its resources as opposed to specific things. And master, you have, so slave is a hot replica of the master. It's the same kind of problems you can have. It's actually, they're both masters, they're both slaves. So the same kind of issues with data redundancy. For MySQL cluster, you have mirrored data. Individual data nodes can fail with aborted transactions. Transactional applications are expected to handle the transaction failures. So the way you architect your application is different for each one of those. So for example, like if you want to put the triggers and whatnot in the database and you're using some kind of master slave or master, you need to make sure your application is dealing with replication safe statements. In MySQL cluster, the application needs to be able to handle transactions that have failed. And we've had, again, experience multiple times with data loss when adding nodes. GALERA cluster, in general, it works by not considering a transaction complete until all of its members agree. So large transactions are not advised, and so you can imagine that if you're sending this as something very large, off to 4 or 5 nodes or more, 10 nodes, and this is a large transaction and you have to wait till everybody agrees before it comes back as completed. So then you can get huge latency with large transactions. That's why large transactions are not advised, and you can have problems that can occur with SST mode, and that's one of the ways that they communicate with each other, those different kinds of modes. So what is best? The problem is that I don't know what your business requirements are. So what are they? That's what you're going to have to look at. You're going to have to look at what your needs are for redundancy, for speed, for failover, all of these things. And also you have cost. Where is it going to be hosted? Are you going to be having your own servers? Are you going to be hosting it in the cloud somewhere? Are you going to be using a hosting service? Are you buying servers? And it depends on your level of expertise. So the easiest is obviously the master and slave and variations. The safest is probably GALERA cluster, but there are some performance impacts there, especially with large transactions that you need to consider. And fastest performance depends on what you're going for. So MySQL cluster could be a solution for you. So could, master, slave, GALERA, any of those. And please don't just don't do a standalone server, one server. That's just very, very high risk. And we have had a lot of problems with people that have called us trying to recover something from a standalone server, and there was catastrophic failure. So please think about what your needs are. Think about which things are best for what. There is no one perfect solution for everybody. There are several flavors of MySQL out there, and they all work very well. They all have pros and cons. So if you need any more assistance with any of these questions, feel free to contact me, and thank you for your time.